Hello everyone, I am Kranthi Kumar, Assistant Professor in the Department of Electronics and Communication Engineering, Marri Laxman Institute of Technology and Management. Today we are going to discuss about the PN junction diode. So how a PN junction diode will be formed and how it will be react in the forward bias condition and in the reverse bias condition. So before going into the analysis of a PN junction diode, so we have to know some basics of some semiconductor materials like p-type semiconductor material and n-type semiconductor material, right? So generally, so the semiconductor is a substance whose resistivity lies between the conductor and insulators. So semiconductors device are, we have two types of semiconductor devices generally. So these semiconductors are divided into two types: intrinsic semiconductors, so these are also called as pure semiconductors, and extrinsic semiconductors, these are also called as impure semiconductors, right? So again, these impure or extrinsic semiconductors are two types. The first one is p type semiconductor material and the second one is n type semiconductor material. So first we have to see about the intrinsic semiconductors. So generally we know that a pure semiconductor is called as a intrinsic semiconductors. In the intrinsic semiconductors, so the number of electrons are equal to the number of holes. So the number of free electrons are equal to the number of holes. So when an electron leaves from one place to another place, so this empty space will be assumed as a hole. So this can be represented with a positive charge. So in order to increase the conduction capability, so we have to add some impurities to the pure semiconductor material. So this process is called doping. So the process of adding impurities to the semiconductor material, which means to a pure semiconductor material, so is nothing but doping. Why? Because so a pure semiconductor material, we have equal number of electrons and holes, so there are no free electrons to conduct electricity. So that's why we, to increase the conduction capability, so we have to add some impurities to the pure semiconductor. So this process is called as doping process. So generally we will use as a pentavalent impurities and trivalent impurities. So let us know which elements are called pentavalent impurities and trivalent impurities. So first, the pentavalent impurities. So the pentavalent impurities are the ones which has the 5 valency electrons in the outermost cell or outermost orbit. For example, bismuth, antimony, arsenic, and phosphorus. So these pentavalent atoms are also called as donor atoms because it donates one electron to the conduction bond for a pure semiconductor atom. Next, trivalent impurities. So the trivalent impurities are the ones which has 3 valency electrons in the valency band, right? So for example, gallium, indium, aluminium, and boron, right? So the trivalent impurity is also called as acceptor atom because it accepts one electron for the semiconductor atom, right? So why we are using these pentavalent and trivalent impurities only as a doping elements? Why? Because the pentavalent and trivalent impurities are used because they create free electrons and holes in the silicon, which means in the semiconductor material, so without disturbing the crystal structure. And they will form a strong covalent bond. So that is the reason we are using pentavalent and trivalent impurities as a doping in the doping process. So next, extrinsic semiconductors. So we know that after adding some impurities to the pure semiconductor, so we will get the extrinsic semiconductor. So a impure, which means it is an impure semiconductor, so which is formed by doping a pure semiconductor, is called extrinsic semiconductor materials. So in the extrinsic semiconductor materials, so we have two types of extrinsic semiconductor material. So we have two types of semiconductor materials. The first one is p type semiconductor material and the second one is n type semiconductor material, right? So first, the p-type semiconductor material. So a small amount of pentavalent impurity is added to a pure semiconductor. To this results a n-type semiconductor material. So the added impurity has 5 valency electrons. So we know that the pentavalent impurity is having 5 valency electrons, right? So for example, if an arsenic atom is added to the germanium atom, four of the valence electrons get attached to the germanium atom, while one electron remains as a free electron. So now this free electron is going to be participate in the conduction. So in n-type semiconductor, as the conduction takes place through the electrons, so the electrons are the majority charge carriers and holes are the minority charge carriers. So if you observe here, so it is the pentavalent impurity arsenic. So it is having 5 valence electron. So 1, 2, 3, 4, and the excess one is 5. So these 5 valency electrons of your arsenic so is forms a strong covalent bond with the your semiconductor material germanium. So here one electron is free. This electron is called free electron. So that is the reason. So the in the n-type semiconductor material, so electrons are the majority charge carriers and holes are the minority charge carriers. Next, p-type semiconductor material. So the p-type semiconductor material will be formed by adding a trivalent impurity to the pure semiconductor material. So we know that trivalent impurities means, so it is having 3 valency electrons in the valency band, outermost shell, right? We have 3 valency electrons. So these 3 valency electrons will form a 3 covalent bonds with the semiconductor material, and one space is here. So this empty space will be assumed as a hole, right? So the empty space will be treated as a hole. So that's why in the p-type semiconductor material, so we will say, so electrons are the minority charge carriers and holes are the majority charge carriers. So let us know the diffusion current. Okay, so when doping is done, so the number of electrons and number of holes becomes unequal. So we added some impurities, right? So this will creates the unequivalence in the number of electrons and number of holes. So these electrons and holes tends to diffuse from higher concentration of charge density to the lower concentration level. So as this, the charge carriers, they constitute a current called diffusion current, right? Next, drift current. So the current formed due to the drift movement of charge particles. So electrons and holes, so due to the applied electric field, so by applying some external electric field, so these charge carriers move from one place to another place, which means maybe the electrons move from n side to p side, or holes will be moved from p side to n side. So this is called drift current. So the drift current occurs by applying some external of electric field. So now p-n junction diode. A p-n junction diode, so is a device. Now we are got some awareness how about the p-type material and a n-type semiconductor material. So by adding these two materials like p and p-type semiconductor material and n-type semiconductor material, then a p-n junction diode will be formed, right? So this is the symbolic representation of a p-n junction diode, right? So it is the anode and it is the cathode, which means it is a positive terminal, it is the negative terminal. So the practical diode is look like this. So this is the practical diode, right? So the p-n junction diode allows current only in the one direction. Right, this is the formation of the diode. So if a p-type and n-type material are brought close to each other, then so a p-n junction diode will be formed. So the diode is an electronic device that conducts electricity only in the one direction, right? So it is the general meaning of a diode. A diode made up of two words, that is di means two, and odd means two electrodes, which means it is having two electrodes. So which means that the device or a component has two electrodes, that is anode and cathode, positive terminal and negative terminal. So we know that the p-type material has the holes are the majority charge carriers, and in the n-type material has the electrons are the majority charge carriers. So one more thing is, so as opposite charges will be attract and few holes in the p-type so move towards the n side, so whereas so few electrons in the n side will move to the p side. Okay, so as electrons and holes move towards the junction. So after adding, so here for example here I am adding p type and n type semiconductor material. So here a junction is created in between p and n type semiconductor material. So as a result, so holes move towards the junction. So some few of the holes move towards the junction, they combine with each other. This creates a region near the junction. It is a fixed positive and negative ions, but no free charge carriers here, right? So this region is called depletion region or junction barrier, right? So we know that, so the major charge carriers in the p type are so holes, and the minority charge carriers are electrons. So in the n type, the major charge carriers are electrons and minority charge carriers are hole. So after adding these two semiconductor material, that is p and n, so that is p and n, okay, so few of the electrons so will try to move, so we try to move towards the so n side, and few of the holes try to move towards the n side. So these electrons and holes so will create a will accumulate near the junction. So near the junction, so this junction will be act as a so depletion layer or a potential barrier. Okay, so this region is also called as so barrier junction, depletion region, space charge region, or a potential barrier. So this is the how it will be formed, because so negative ions on the p side, so and positive ions on the n side will be formation of a narrow charge region, and each side of the p-n junction diode. So this region is called a depletion region or a space charge region. So now we are going to apply some external voltage to the p-n junction diode, and we are going to be analyze how the diode will be react. So when here, so if you observe this diagram here, I am not applying any external voltage to the p-n junction diode, then so no current flowing through the diode. So next, okay, so next, so now the forward bias condition of the p-n junction diode, so right, so it is the p-n junction diode, so p and n. So when we are connecting a p type semiconductor material to battery positive terminal and n type semiconductor material to battery negative terminal, then we can say that so this is a forward bias condition of a p-n junction diode. So now what will happen in the forward bias condition, right? So the immobile ions which are accumulated in the depletion region, so will not move to the either p side or n side. So that's why we have to apply the energy more than this electric stored charge energy, right? So we have to apply more voltage to the p-n junction diode, so to remove this depletion region, right? So after applying some external voltage, so now, so this here we are connecting so p type semiconductor material to battery positive terminal and n type semiconductor material to battery negative terminal. So we know that so in the p type semiconductor material, so the majority charge carriers are holes, okay. So we know that so one positive charge and negative charge will be attract, so positive repulsive, negative repulsive, okay. So here the in the p type the majority charge carriers are holes. So here we are connecting p type material to battery positive terminal. So positive means so these will create a repulsive force on the so charge particles which are present in the p type material. In the same way, so in the n type semiconductor material, electrons are the major charge carriers. So here we are connecting to this n type semiconductor material to so battery negative terminal. So negative means a repulsive force will be created. So now this leads to so move the electrons present in the n type semiconductor metal will move towards the p side, and so the holes present in the p type semiconductor material will move towards the n type semiconductor material, right? So this is the expected waveform in the forward bias condition. So during the forward bias condition, so right, so if this is a 0, so if you are increasing the voltage, so up to this point, so the depletion region will not be vanished. So at 0.3 volts for germanium and 0.7 volts for silicon, so the current flows starts. So this corresponding voltage is called knee voltage or cut-in voltage, which means it is the small voltage where the current flow starts in the diode. If you are using a silicon p-n junction diode, then the current flow start at 0.7 volts. If you are using a germanium p-n junction diode, so then the currents flow start at 0.3 volts. So later if we increasing the voltage, then so there is a rising in the current. So in this region it will accepts the Ohm's law. If you are increasing the voltage, then current also will be increased proportionally. So this is called so forward bias condition. So next, reverse bias condition, right? So when you this is opposite to the forward bias condition. When we are connecting a p-type material to battery negative terminal and n-type material to battery positive terminal, then it is called so reverse bias condition of a p-n junction diode. So what will be happen in the reverse bias condition? So the majority charge carriers are in the p-type semiconductor material are holes, and majority charge carriers are n-type semiconductor materials are electrons. So these positive charge particles attracts toward the battery negative terminal, and these electrons will be attracts towards the battery positive terminal. So this may leads the increase the depletion layer width. So this will leads the increase of the depletion layer width. Now the charge carriers will not move from inside to p side and p side to inside. So in the reverse bias condition, very small amount of current will be flow, that is due to the minor charge carriers. So in the p type, so electrons are the minor charge carriers. In the n type, holes are the minority charge carriers. Due to these minority charge carriers, a small amount of current will be flow in the reverse bias of a p-n junction diode. This is the formation of a p-n junction diode in the reverse bias condition. So if you analyze the graph, so in the reverse bias condition, so if you are increasing the reverse voltage, a small amount of current will be generated. So that is called so leakage current. That is called leakage current. So if we increasing the reverse current voltage further, then the diode may release the so high voltage. Okay, so the diode may so generate high current, so and it will be damaged. So at what voltage the diode is producing high current, so and it is going to be damaged, the corresponding voltage is called so reverse breakdown voltage. At this voltage, so the diode will produce high leakage current, and so we cannot control the flow of current, and the diode will be damaged. So that's why that's why we are saying a p-n junction diode will be conduct in the only in the forward bias condition, and it will be act as like a insulator in the reverse bias condition, which means the flow of current only in the one direction, that is in the forward bias condition, right? So it is the general equation, current equation of a diode. So id is equal to is into so e power vd by neta into v by neta minus 1, right? So here veta is the thermal voltage, is means the reverse saturation current, and vd is the applied forward voltage, right? Okay, thank you everyone.